Okay, let's look at the solution. Example number 1. Asteroid with a mass of this approaches the Earth if they are this much apart. What is the asteroid's resultant acceleration? Okay, so we want to find how fast is the asteroid moving towards the Earth. Okay, first, where do we start? We find the gravitational force first. Okay, we have two masses. One is the asteroid, one is the Earth. We are going to assume that they are point masses. So we take the center of the asteroid to the center of the Earth. The distance is this much, right? So F equals to GMM, M1 and M Earth R squared. 6.67, 10 minus 11. Okay, the gravitational constant, so times by 10 times 10, 15. The mass of the Earth, how much? 5.97 times 10 power of 24. Okay, over 250,000,000 square. 达到多少？6.37乘10 power of 13 Newton。OK， 这个 force 是 experienced by 两个 object， Earth 还有 asteroid。那我们可以用这个 force 来算 asteroid 的 acceleration。F 等于 ma， 这个是 mass of the asteroid。Acceleration equals to 6.37 除以它的重量，等于6.37乘10 power of 减3。ms minus 2. Okay, that's the answer. Number 2, two asteroids exert a gravitational force on one another. By what factor would this force change if the one if one asteroid double in mass, the other one triple in mass, and the distance is quadruple? OK， 意思说是还是讲 force equals to GMM over R square。如果一个 mass double， 然后另外一个又 triple， 然后那个 distance quadruple， then 那个 force 会是什么？会变多少 ？Okay, what is the factor of the change? So how do we solve this? Okay, we do some expression like this. Okay, we start from the original equation. This is the original force, right? Experienced by this much of mass and distance. So we write a new one, new f prime, okay, f dash. So f dash is equals to g, the new m1, the new m2 over the new r square. Okay, then we substitute inside. Continue here. F dash equals to g. The new m1 would be, okay, let's say m1 is the one that is double in mass. Okay, so the new m1 would be 2 m1 double in mass. 然后再乘进去那个 triple in mass 的，所以是3 m2 除以那个4倍的那个distance 啊，所以是4r square。OK， 等于 factorize 出来6g m1 m2 over 4，我 square 那个4是46，然后我们 r 还有 square。OK， 继续这边，所以是 f prime 6除以16 g m1 m2 除以 r square。 这边怎样做？我要看它是多少倍 of 那个 original force 嘛，对不对？所以我就要 sub 这个 original force 进去咯。original force 是这个 ，OK， 我 sub 这个进去 ，GMM over R square 就是这个整个东西了。所以是6 over 16 F dash 越减这个236 286 F dash F，OK，F dash 是什么 ？F dash 就是你的新的 F，the new F is equals to 38 of the OF。So that is your answer. Okay, then you can calculate lah. If the OF is how much the force? Okay, 2 times 10 power of 7, let's say. Then you can calculate what is the new F. It's 3/8 of it. Then it would be 7500000. Okay, this is just an example lah. Your answer is this one. Number 3, astronaut lands on a planet with the same mass as Earth, twice the radius. What will be the acceleration due to gravity on this planet? Okay. This is very similar to example 2. Okay. First, we find the force. GME. OK， 这样子啊，看啊，这个它是要讲 what is the acceleration due to gravity, right？ 所以它要找的是 G， 不是那个 force 啊。所以我们用 G 的 equation 哦。G 的 equation 是什么？刚刚我写 GME over R square 对吗？这个是我们的 G equation。G 的more general equation. Okay, you have a lot of equation for G, like W equals to mg. Also, that is, you can say G is equals to W over M. Okay, but this one is we use it for the gravitation. Okay, so you can see G depends on two things. Depends on the mass and depends on the radius of the planet. 所以如果那个 planet 的 radius 越大，是你的 G 是越大。Okay, so from here, how do you find this? Okay, when the planet that he lands on is twice the radius. Okay, so then I can write G new. What is my G new? Equals to GME. It's the same mass, right? The new planet is the same mass as Earth, but it's twice the radius. So we do like 2R. 2R squared. So equals to G new and GME over 4R squared. So G is equals to 放它出来 1 over 4 GME over R squared. 继续，这个整稿东西就是我的 G， 放进去 ，OK。Then 你可以找到 my new G is equals to 1/4 of the gravitational field strength of the Earth. That is your answer. Okay, let's go to the next part. Okay, here's the question. You see, how come the satellite is moving around the Earth, right? So this is the Earth, and we have the orbit of the satellite. How come the satellite is not falling towards the Earth, and it is able to revolve around it without like drifting off, without drifting away and falling towards the Earth? How come it can maintain in its orbit? How do objects keep themselves in orbit? Just like the Earth rotating around the sun. How does the Earth keep itself in orbit? How does other planets keep themselves in orbit? Okay, so you see, there's something that we call the linear velocity. Okay, linear velocity. Imagine that this satellite is constantly moving in this direction. In this particular instant, it is facing here, right? It's moving in this direction. Okay, the next second it will change, right? Because after some period of time, it is now here. It's now here, and then the velocity would be facing here. Okay, this velocity, we call it a tangential velocity. Tangential. Why we call it tangential? Because it's tangent to the circle. If you draw the radius from here to here, you join a line, straight line here. This is the radius of the orbit, okay, of the orbit. And here also I draw a line. This is also the radius of the orbit. And this velocity is perpendicular to the radius of the orbit. And it's tangent to the circle. So we call them the tangential velocity. Or sometimes you will see the word linear. Linear velocity. Okay, so we have two types of velocity here. Linear and the orbital velocity. Orbital speed. Okay, orbital speed 就是很像它 measure 它的 revolution in terms of the revolution. OK， 就很像比如说 speed 是等于 distance over time， 对吗 ？OK，so 如果我要找它的 orbital speed then 我的 distance 我会放 the circumference 的 distance， 就是你的这个 orbit 的 path 的 distance。OK， 也就是 2πr， assuming that 你的 orbit 是圆的，可是真正它不是perfect circle So it's close to a circle, so I can say that the distance that the satellite moves one round is 2πr. Okay, so one round and divided by the time taken for one revolution. We call it as period. This is period. Period is time for one revolution. Okay, so 你就拿到这个 formula， 这个 formula 是我们叫它 orbital speed of the satellite. Not only satellite, it can be applied for planets. Anything that is moving around something, you can calculate the orbital speed, this one. Okay, so this is the first type of calculation. The second type is the tangential or the linear speed. Is this one that I'm referring just now. Okay, the linear speed is different. It is facing this way, and it is changing. Okay, now back to the question just now. Back to the question, how does the orbiting object keep themselves in orbit? Is because they have this linear speed. It's because they have the linear speed. And the linear speed is enough to keep them from falling towards the center of the Earth, and not large enough to keep them from drifting away. Okay, if you know what I mean. Okay, I repeat. The linear velocity is just right. It's just enough to keep them in orbit, without falling off and without drifting away. Okay, so imagine that this satellite is constantly trying to escape from the orbit. Okay, this is the way I imagine it. Imagine that it is constantly trying to escape because of its linear velocity. Okay, imagine suddenly, if suddenly the Earth loses its gravitational pull, then this satellite would move in this direction, right? It will continue moving in this direction based on what is the initial velocity direction, right? Okay, the moment when it loses its gravitational pull, if it's facing this way, then the satellite would continue to move in this direction. Okay, but because of the linear velocity and because of the gravitational pull, so every time when it tries to escape in this direction, it is being pulled to one side. So this creates a curved path, a curved movement. Okay, so instead of going straight here, it will go here. It will curve inward like this here. Okay, so this happens at every instant. Here being curved and it tries to escape again. Tries to go in this way, then it is being curved inward again. It tries to escape in this way, it being curved inward. It tries to escape in this way, it being curved inward. So this creates a orbital path, a circle. Okay, so meaning that here the gravitational force is being cancelled off by the linear speed of the satellite. Okay, so this is how you get orbits. That's how orbits forms. Okay, now you see, the satellite, right? At one stage, the satellite loses its fuel and it falls towards the falls down to the Earth, right? So what happens is that as it loses its fuel, okay, when its lifespan reaches, then it loses the linear velocity. The linear velocity will decrease. So when the linear velocity will decreases, then it doesn't have enough velocity to keep it afloat. So it will start spiraling into the Earth. So the trajectory would look like this. It will go like this, spiral around like this, and then slowly it will go, fall down to the Earth. Okay, this is when it reaches the lifespan of the satellite. Okay, why this happened? Because it doesn't meet a minimum requirement of the linear velocity to keep itself up there. Okay, there's a minimum velocity required. How do you know what is the velocity? You can actually find it, you can calculate it. Okay, how? Okay, you see here. Okay, now before we go to the velocity stuff, I want to point out a few things. Is that you see, when the linear velocity is changing in terms of the direction, okay, not the value. The value is the same. It is moving at the same speed here, but the direction is changing. Now, if you remember, I talked about this one in the last lesson, right? I talked a bit about this one. When you have a changing velocity, let's say this is the radius. This is the orbit of the satellite. This is the radius of the orbit. So the satellite is here, the velocity is here, v1. After some period of time, it is here and the velocity is here, v2. If you add up this one, if I want to calculate the change in velocity, which is the acceleration, okay? Acceleration equals to change in velocity over time, okay? So to find the change in velocity, I take the v2 minus v1, okay? v2 minus v1. So how do we minus these two things? These two are vector. They are vector, meaning that they have a direction. For scalar, it's very easy. When you minus, you just minus the value, right? 5 minus 3, 3 minus 5. But for vector, it's different. When you want to minus, you have to draw a diagram. Draw a diagram showing the vector addition. Okay? So how do we draw this? Actually, you see this V2, we just take the direction of it. V2 is facing this way, so I will take V2 like this. Okay, so V1 is like facing this way, right? So facing this one, if you have a negative v1, then we invert the direction. We change the direction because it's a negative vector. Okay, so this one is initially it's facing here. So if it's negative v1, then we invert the direction like this, v1. Now it's facing this way. Okay, it's facing this way. Okay, but they will not ask you this one now. Okay, they will not ask you this one in the exam. Okay, I just want to give you a bit of this. You will learn this. You will learn this in the coming chapters. Okay, so now when you add these two vectors, you get something like this: v2. The nose add to the tail. This is v1. Okay, the nose of the first vector, the tip, is connected to the tail of the second vector, which is this one. So I draw like this. Okay, so think of this like a journey. You start here, you go here, you go here. So shortcut, you can also go like this, right? This is the shortcut. And this is the change in velocity. Okay, in other words, I can say this is actually a v2 minus v1. Okay, so just pay attention to the direction. Okay, I just want you to know the direction. Okay, the direction is pointing this way, right? So it's pointing like this towards the center. At this point, it is pointing towards the center. At this point, it is pointing towards the center. Here also, it is towards the center. So the acceleration is always towards the center. That is the bottom line. Okay, the point I'm trying to make is the acceleration is always facing towards the center of the orbit. And this acceleration is we call the centripetal acceleration. Okay, and centripetal acceleration occurs for all objects that are moving in a circle. Any objects moving in a circle, they will experience centripetal acceleration. Even you sit in a car, you go like the roundabout, right? Also, you feel this centripetal acceleration. It's like you are pulled to one side. You're pulled to which side? Towards the roundabout, right? To the center of the roundabout. Okay, that is also centripetal acceleration. Okay, now, so from here, centripetal acceleration is equals to, there's a formula for this, v squared over r. Write this down. Okay, write this down. V squared over r is the centripetal acceleration. V is what? V is the linear velocity. Okay, it's the linear velocity. Okay, so if A is v squared over r, then we can put it in the F equals to ma. So I get mv squared over r. And this, what we call this? We call it the centripetal, centripetal force. Okay, the centripetal force, the force that is pulling it towards the center. So for the planets, for the satellites, they orbit around the Earth, they experience a centripetal force. Okay, why doesn't the centripetal force pull them towards the center of the planet? Pull it downwards, pull it towards the Earth. We already talked about that one, right? Because of the linear velocity. Okay, but if it loses the linear velocity, then it will start to fall down. Okay, so all orbiting object experiences this one. And this one, I can also say that the centripetal force is equals to the gravitational force. This is the one thing that you need to understand. The centripetal force is equals to the gravitational force. Okay, so from here, we can do a little bit of mathematics. Okay, centripetal force is mv squared over r equals to gravitational force is we already know that GMM. This is the mass of Earth. This is the mass of the satellite. Okay, divided by R squared. This is mass of satellite. And then cancel off the mass. We get V squared over R equals to GME over R squared. 把这个搬过去对面，我们 cancel 买那个 R， 所以我们拿到 GME over R。到最后我把它放 square root GME over R。Then 我拿到这个东西 ，this one you need to take note. This is what is this? V, linear velocity, right? Linear velocity. With this formula, you can calculate what is the linear velocity of the satellite that is currently orbiting the Earth. And you can see this linear velocity depends on the mass of the Earth and the radius, meaning that how far it is up there. Okay, the radius measured from where to where? From the center of the Earth. Okay, always from the center to the satellite, not from the surface. You have to add the Earth radius. Okay, for example, they ask you to calculate, okay, what is the linear velocity of the satellite when it is at, okay, this is the satellite, this is the Earth. Calculate the linear speed of the satellite when it is at altitude of 20200 km. How fast is it is moving? The linear speed. Okay, so we draw like this. This is the orbit. Moving this way, right? Okay, then you can put in the formula. So V equals to square root of 6.67乘10 power of 减11，再乘 mass of Earth. Okay, mass of Earth 是 5.97乘10 power of 24，这种它都会给的啦。OK， 这种，可是那个 gravitational constant 你要记得 6.67。OK， 5.97乘10 power 24，再除以，那这边是要小心，这边 R 是什么 ？R 是20200吗？不是啊，很多人做错就是因为这个 ，OK，common mistake。R 是20200，你要换去 meter， 所以乘10 power 3，然后你还要再加那个地球的 radius，OK， 6400000，因为6400是 km 啊 ，km 换去 meter，OK，so 20200换去 meter， 再加6400换去 meter， 那个是你的 R，OK，measure from the center of the earth，so calculate your V， 你的 V 你拿到 3.87乘10 power of 3 meter per second. This is how fast the satellite is moving. It's about 3870 meter in 1 second. If your satellite does not attain this speed, it will not keep in orbit. It will start to fall down, spiral in a spiral manner like this. Eventually it hits the Earth. Okay, this is the minimum requirement for it to be up there. Okay, formulas to remember is this one. F 等于 mv square over r， 这个是 centripetal force， 然后你要知道就是 centripetal 是等于 gravitational， 还有你要知道这个 linear velocity and also the centripetal acceleration and also this one orbital speed. And of course the GMM, that one also. 还有什么？还有G 等于 GM mass of Earth at Earth radius. This one is 1. And the very general one, this one. Okay, so these are the formulas that you need in the calculation. Okay, will we create a link and we'll do some exercises. I'll send you some exercises.